Machine learning and robotics, and today he will describe recent advances in autonomization of fiber hemp cultivation using AI-assisted agricultural robots. So Marek, welcome to our virtual stage.
Hello, good morning. Thank you for the invitation. That's the first thing to say, because I think it's kind of unusual for me to be in a crowd of experts that's mostly concerned with agriculture. Let me share my screen. Hope you can see it.
Yes, we can see it.
Okay, so let's start then. My name is Marek Kraft, and like Agnieszka was so kind to introduce, I'll talk about autonomization of fiber hub cultivation using AI-assisted methods with robots. First, a few words about where I come from. I come from Poznan University of Technology in Poznan, Poland. I'm with the Institute of Robotics and Machine Intelligence, and specifically Computer Vision Lab. And we as an institute, in our research, focus on intelligent autonomous machines for different purposes. And in case for those machines to perform those tasks, we do with perception, planning, and also action. Everything with the extensive use of the so-called AI. Basically, it's still supervised machine learning, albeit more advanced. And as you can see, we deal with all kinds of tasks and robots, like underground structure exploration using legged robots, help with tedious manual tasks using this mobile robot that's actually also equipped with 2 hands. But also autonomous vehicles, because from our point of view, they're also robots. They're basically robots on wheels. We work with a range of sensors, from cameras, depth cameras, to LiDARs, thermal data. And we also try to mount our sensors on different devices, like the robots I've shown you, but also on drones. Here's an excerpt from our recent work on the assessment of damage that was caused by wild animals to cornfields in Poland. It's useful from the point of view of insurance, but we also do a lot of other things like land cover segmentation, plant health assessment, etc., etc. Generally, we try to do this using onboard processing of the gathered data to provide the information that's useful from the point of view of the agriculture. I also decided to include this slide because we also performed some work on pedestrian monitoring in terms of counting and the behavior analysis for traffic management, but we were recently contacted by someone who was interested in adopting those methods to actually monitor the behaviors of grazing animals. So that might be of interest to you in terms of what we do. This work, the results that I'm presenting, were mostly a result of a funded project, which was realized by a consortium. So aside from us, there's our consortium leader, which is the Invebit company, which is basically a high-tech software house with vast experience in a range of projects, ranging from energy systems like virtual power plants, hydrogen energy, robotics in the traditional sense, not agricultural. They did a notable part of the software for a caretaker robot that's also AI powered. A lot of Internet of Things projects. One of them was, for example, beehive monitoring that was using a range of sensors to monitor the behavior of bees and the well-being of bees. Smart cities, such as public space monitoring, that's actually how we got in touch, but they're also very active in the field of e-agriculture, also agriculture robotics, like this project, but they also recently won a grant for apple picking robots, so kind of say that they're also specialized in this field. Since we are more IT related, and so is our consortium leader, we also obviously needed some expertise in the agriculture side of things. And our third partner, the final partner, is the Institute of National Fibers and Medicinal Plants, which is conveniently also located in Poznan. It is a state-funded research institution that deals with all kinds of fibrous and medicinal plants, their cultivation, development of new cultivars, finding interesting uses for those plants in terms of medicine, but also in other areas of of economy, and they also serve as consultants for government, sorry, and commercial companies regarding those herbal products and food products. Obviously, hemp is within the range of their interest since it's both a medicinal plant and a fibers plant. So, with these introductions aside, what is the goal of the project and what was its motivation? So, hemp products are very useful in a variety of applications. I think this is a plant that was kind of rediscovered in recent years because it has a lot of uses, ranging from natural fibers that can be used to fabric garments, but also used in construction for isolation materials. They can be used as biofuel, they can be used as food, as a source of nutrition. They can be used to produce seed oil, but also plant oil. So they're very, very multifaceted in terms of their potential uses. And as you grow hemp in really quite a lot of applications of hemp, pollination is a really big problem. For example, if you cultivate hemp for biomass or cannabinoid content, that is oil extraction, you can get severe economical losses from the plants being pollinated. So this is also interesting from the points of view of actually selling the seed materials, because feminized seeds are very desirable. Usually you buy seeds that are really low in male seed content, right? Also, the rogue pollination is a serious problem, because even if you're not concerned with your plants being pollinated, because, for example, you grow them just for fibers, your plants might pollinate the plants on a neighboring field. So generally, it is not desirable to have male plants in your field. You try to remove them, and it's usually performed by hand. So someone walks around the field, identifies those plants, and just pulls them out. They're subsequently being burned. It's a tedious task that needs trained staff, special handling, and special arrangement of crops. This is sample images from the field with male plants and female plants. Male plant here, here, and here. You can see that they can be discerned by the shape of the flowers, which is crucial. And this is also the way that we later try to recognize them. So with this in mind, we thought, hey, we could use robots for that, right? I'm a roboticist, at least in part. I deal mostly with vision processing, but I'm familiar with robots. And robots make our life easier in terms of removing those tedious tasks. So how would this robot look like? So people need access for manual plant removal, and tall plants require dense pads. We work with Henola variety of hemp, and their height is between 2 and 2.5 meters, and they're considered some of the lower varieties of hemp. So generally, you have quite dense arrangement of pads when you cultivate hemp, so that people can access those plants, that they actually see them if they need to remove those male plants. And that is obviously not optimal. So if we could make a robot operate from above, that would give us the benefit of automation, but also the added benefit of better yield in terms of better density of the plants per unit of surface of the field. So what we came up with is quite a typical arrangement for an agricultural robot. This is this inverse U-shaped arrangement that deals with the plants that are basically running below this robot. The thing that is kind of different is that this robot is big. I don't think I have seen one that's similar in dimensions, but we deal with really big plants, so that was necessary. And this mobile robot base is pretty universal. This can be used for not only the task that we had in mind, but can be adapted, for example, for spraying, or equipped with different end effectors. It can perform also other tasks. So this is something that we had in mind for this robot, and this is how it would look. But this is just the mobile robot base that's capable of moving around those constructed paths. But we also need very, very precise handling. hemp plants are very sensitive to herbicides, so spraying a plant once we find it is not an option, because like several square meters of plants would be dead just from applying something to a plant in terms of spraying. And pulling those plants out is also not an option. We were considering that, but we've come up with something that we thought is a better solution. I'll talk about this a bit later, but in any case, we need to place an arm on the robot. As you can see, there was this also special plate envisioned in this construction so that the arm can be mounted on top. This robot arm, similar to this robot, were actually commissioned. It is not something that we did. It was actually commissioned to be put together for the purpose of this project. The robot arm has quite a big reach. It's not a typical robot arm in the sense that it doesn't have a sub-millimeter accuracy. It doesn't move very fast. But for the purpose that we wanted to, what we wanted to perform, it's perfect actually, because it's very light, it's very low cost, and it has a great reach. So the arm is generally mounted on top of the robot, and since spraying and pulling is out of question for different reasons that I mentioned before, we needed a custom special end effector, and after consulting the experts from the National Fibers and Medicinal Plants Institute, we decided that we'll go with a gripper that will inject the herbicide directly into the plant. And this is the first prototype. It's a CAD model, basically. But this solution minimizes the use of chemicals. Basically, you need between 1 or 2 milliliters per plant. And it also facilitates very, very individual treatment so that no other plants in the field are affected, beside the ones that you want affected. So the general concept is that our robot moves around within this field using those predefined paths. And once it encounters the male plant, it can obviously detect it using the base-mounted sensors, which we envision to be RGBD cameras. Then we can roughly position the arm to align with this plant, and then the plant arm takes over control and perform some kind of visual severing to grab this plant, inject this herbicide portion, and then basically we hope the plant will be kind of neutralized or eliminated, and then the robot can move forward until it encounters another plant to be treated. So with this planning done, we thought we have everything thought out, and now it's just easy peasy. Well, maybe not easy peasy, but the planning stage was over, and we were very eager to get to work, but turned out not to be so easy. This is a project that was really started in difficult times. The international situation, the COVID situation, has really hit us. There's been really difficult problems with the shortage of components. So, for example, I'm still waiting for some cameras that I ordered a year and a half ago, and the estimated ship date is May 1st. But it was delayed so many times that I'm not even sure that if I get them. But that's okay. We'll find some alternative solutions. But even with things that were available, they were getting quite expensive. The lead times for the things we ordered, as the robot arm and the mobile robot base, was also getting longer. If anything got broken, you had to wait for the components to fix it, and it also took time. So we're quite a bit behind schedule and seasonality of our problem, because we can obviously only work when the health plants are at least partially developed, is also adding to this. So we had the robot completed basically late autumn. So, we can't do a lot with it right now because there's no hemp plants to treat. This is also partially affected by this price hike in terms of heating costs, because we were thinking of having at least some plants available for testing, but heating costs have grown 5 to 6 times, and therefore we can't afford a greenhouse. The project budget is just, not allowing that. But bear with me, we did not give up, and right now we're getting in the second part where I show you what we are actually capable of completing. And so we got the robot basically needs some kind of brain. Actually, our robot has 2 brains. One is typical PC, embedded PC that is in a rugged enclosure, enabling it to work in tough environmental conditions with many ports. So it's a standard PC in the sense that it's hardware-wise like your laptop or a computer you have at home, and we use it for system-wide control that is driving, getting the sensor data, and getting the robot to react to the external conditions so that it can perform the task of driving around the field. And the other brain is specifically used for those AI workloads that are mostly, having to deal with the need for processing images. And this is a NVIDIA Xavier NX embedded board that has some AI accelerators built in, so that those algorithms are actually performed at a speed that is real time or near real time, so that we can actually perform this task as the robot drives around or as the end effector moves. Everything's integrated under ROS, that is Robotic Operating System, which is a standard in robotics, basically, in the robotics industry, which enables us seamless integration of different sensors, different algorithms, etc., etc. So it's a really nice things to have, and we also have experience in using that. So we decided to go for that. Aside from the capability of driving on and kind of thinking, the robot has to have some sensors, and so the robot base is fitted with dual GPS, that is RTK GPS, that is precise to under a few centimeters, so we can also get robot frame twist, so kind of heading of the robot if we use two of those. It has dual mounted RGBD cameras for the detection of male plants that are mounted on the robot base, and also two LiDAR sensors that are used for navigation in terms of like getting in the middle of those paths that are created for the robot to drive around the field. And like I mentioned, we didn't have much to work with for quite a long time because of the days, but we still managed to, since we have the CAD models, to perform a lot of simulation experiments, like control of the robot that drives around, performs certain tasks along a specific path, how it reacts to different sensor input. So like time wasn't wasted. Well, still wasn't a perfect situation, but when the robot actually came in, we were ready. And as you'll see, we are able to get the robot to do what we wanted. Like it can go along the specified path. It also reads the LiDAR sensors, which basically show you the yellow dots that are aligned with the arrangement of walls within this garage that we keep the robot in. So basically, we're able to get the robot to drive a certain path and to react to the sensory input, which is nice. It's basic for this field navigation. Our work on detection of male plants was also started in simulation. As you can see, we were able to put together quite realistic-looking plants that we then used as a source of image input for the detection algorithms that we're training. The algorithms is mostly based on YOLO family of detectors. And the first tests were conducted using simulation data, but then we switched to real data. As you can see, the real data looks much worse, but it's also some kind of problem with lighting, because it was some plants that were just grown indoors. And the results that we got from indoor plants were actually quite satisfying. It's obviously not something that will completely substitute getting into the field, because, well, the transferability problems were discussed vastly in the previous presentation. So that we also envisioned to have this problem. But we're able to get over 90% accuracy in plant detection. It's MAP at 50, which means that we only consider detections that have at least 50% overlap of bounding boxes that are hand annotated, that is ground truth, with the bounding boxes that are actually detected by the algorithm. So I think we could even go a bit lower, but it's decent overlap, and it's a kind of standard method that's used to measure those type of algorithms. And the MAP, basically AP, because we only have one class, that is those male hemp flowers, is over 90, which means that is the area under the like approximated area under the recall precision curve is 0.9, with 9 being perfect. So we're quite happy with the results that we got, and I think it's a good starting point for trying to find those flowers in the field. So this component aside, we are able to find plants. We also need to grab them, as mentioned before. And these are the first models of our end effector. We went through a series of prototypes, and now the prototype that we're happy with is mounted on the arm and is also already being used in grossbeam experiments, also being integrated into ROS. And we did a series of experiments that confirmed that it's actually able to grab an elongated object and inject a measured portion of some liquid into it. This is how it looks. As you can see, it's mounted on the arm, and the arm also is equipped with RGBD camera that provides visual input for the algorithms that we'll discuss later. Yeah, and it's I think that we went through quite a lot of prototypes, and we tried to envision any problem. For example, we had some problems with plants being stuck in those needles or like on those needles. But the most recent version, as you can see, as it flexes, it presses the plant against those needles, but as it extends back, it like kind of pulls aside the plants from those needles. So turned out to be the solution to our problem. So we're able to grab the plants and inject the herbicide. We're able to find them, so we need to grab them, right? So we need to know where to grab, actually. So we prepared a diverse data set of images that were annotated. Those stems aren't actually red. Those are annotations that were performed by our staff. And the data set consists of indoor, outdoor collected images, but also some simulated images. And we tried a few of approaches. First was when our data set was still small, convolutional neural network with two linear inputs for the angle and the location of the stem in the middle of the image. But then we quickly turned to some segmentation-based methods that you can see here. The stems are successfully detected. But recently, the best results we got were actually also using those algorithms from the YOLO family. They can also be using a version that performs detection, but also segmentation within bounding boxes. Everything is integrated in ROS already, so we can just mount it on a robot and it should work, but it hasn't been tested yet. We chose YOLO because even though the F1 score, DICE score for single class segmentation is not that great, but we're having a lot of really tough cases in our data set. As you can see, the stems in here are really small. Not all of them are being detected. It obviously impacts the F1. Also, some of the pixels that are assigned to the stems by the annotators are not perfectly aligned with the detections. It's also impacting the accuracy. But the algorithm's errors mostly in difficult cases, and the errors it makes for the easier cases are easy to tolerate. As you can see, if you really approach the plant and we're really close, the stems are well detected quite reliably. So we decided to go with that. And with this segmentation result ready, we're able to project this segmentation result on our depth image, because what you see here on this manipulated RGBD camera, so basically you get a 3D location of the stem from that. And using this 3D location, you can locate this stem in space and use a visual servoing algorithm to generate a trajectory that if the robot follows it, it will eventually end in a position that would allow us to grab this stem. Since it's quite a dynamic environment and the plant can be kind of displaced, for example, by gusts of wind, we provide visual feedback at 10+ hertz, so the gripper and the arm can adapt to the changing pose of the plants. And here's how the process looks. Might not be obvious from what you see here, but actually, yeah, it's confirmed that the robot adapts its orientation and position to the position of the detected stem. It was looking nice in this video. We have performed quite a few other tests that confirm that even with multiple stems and like more challenging backgrounds, it performs quite well. Obviously, it does not, I don't know, like, it's not a substitute for real life tests, but we need to wait for them. We're actually waiting for spring and then the summer to actually be able to work on real plants. So those elements that were shown here are already operational, and we will now come to the summary. So although the project is delayed for for other reasons that were mentioned before, parts of the system are operational, and we actually started working on integration. So we will be mounting the arm on the robot next week. We'll be driving around with the arm, trying to grab those plastic plants that we have at the level at which it will actually reside, right? So the arm will be mounted on top of the robot. We really didn't expect that this will be so hard. Like, I knew that working with hardware is hard, but what's really happened, it exceeded our expectations. It's a quite complex project with a lot of moving parts, and we're not using standard components due to cost and also due to the fact that we had to adapt to the problem at hand, and that caused other problems. But the individual part of the project are actually performing as we intended them. So plant detection, stem detection, grasping, injection, and parts of the navigation pipeline are accurate enough, but it was done in partially simulated or artificial conditions. So obviously need to correct for that once we get into the phase of field test that will hopefully come after this next spring. We hope to have this robot ready in the spring, late spring. It should be just ready to roll out in the field. And once the hemp plants grow big enough in order to be graspable, or in order to perform an environment that we can traverse or try to navigate in, we'll just start to work in this realistic conditions. So that's it from me. I hope that was kind of interesting to you, because like I said, I'm not agricultural expert. I also obliged to mention that the research was funded by the Polish National Center of Research and Development. And if you like the results of our work, I invite you to visit our webpage, or if you want to discuss some issues that are related to it, please contact me directly. My email address is given here. Thank you.
Thank you very much, Marek. It was a great presentation, and I learned a lot. I'm more on the life science part of the world, so talking about robots is very interesting. We are still waiting for questions in our Q&A box, and I suppose everyone is in a dire need of a coffee. But before we can go to the coffee, I've got a few questions myself. So what do you think, what is more difficult? Training a vision processing model for the stem detection, for example, or programming of the robot or building of a robot? Which part is more difficult?
I would have to say that building of the robot. Also partially because of the fact that in terms of vision processing, I usually know what to do, but when this robot construction came up and it had to be built according to some specifications, that was actually resulting in quite a big construction that was hard to make due to the aforementioned problems. That was really problematic. And also, I'm not an expert on navigation per se, so I trust my colleagues. Obviously, this whole is a result of work of a large group of people, and the excerpts that I've shown you that deal with vision were actually done at our lab. But this navigation part that's been done by a partner, and also a vast body of work that was performed by our partner, this Institute of Fibrous Plants, that they try to come up with a herbicide that would on one side be least harmful or toxic, on the other side will perform well. And they also work with this different arrangements of the field. It was all coming together. So I still would say that the construction of the robot and programming of the robot was the hardest thing.
Thank you. The design of the robot actually reminds me of maybe another thing that could be done, pollination in the field, because I remember going into the field and pollinating some plants, oilseed-rape plants, and I suppose a similar design that you have could be applied for this purpose probably. So do you intend to try to maybe branch into other projects that could use this design?
Yeah. As I mentioned, it's quite universal. We actually the Institute of Fibrous Plants and Medicinal Products has a vision for using this for spraying the kind of sticky substance that's based on sugar, so that the seeds won't fall off the plants, because quite a lot of seeds get lost in the harvesting process, and as the plants get ripe, obviously they're not ready at the same point in time. And they say that's been quite a few experiments in spraying them with this sticky substance, and it also like helps to increase the yield in terms of the number of seeds, or the weight of seeds you collect, by 20 or 30%. I think that in terms of pollination, I've seen a robot similar to this one. It's actually equipped with ventilators that were creating strong gusts of wind that would blow the pollen from some flowers, and that would pollinate other plants in the vicinity. So yeah, there's quite a lot of applications of this arrangement, of this typical type of robot. I think that it is still to be explored. Obviously, we need to finish with this one.
Thank you. Are there any more questions, maybe from my co-chairs? I was wondering about going into the field, because the field is always very heterogeneous, as Jerome as well mentioned. I would expect there might be problems with wind moving the plants, if this could potentially impair the gripping of the robot on the stem. Do you have something developed to counteract?
I think with this update rate of 10 Hertz, since we use visual serving, it's not a one-shot process where you try to see where the plant is and just follow trajectory that's predefined. It's an adaptable process that updates every 10th of the second. So with small gusts of wind, I think we'll be able to deal with that. With strong gusts of wind, I'm not sure. But with this arrangement of plants, actually unpollinated hemp is actually quite dense. It's not so easy penetrated by wind. So it's also mentioned by our partners. So we hope that, obviously we can't imagine everything, but we hope that what we did for now will suffice to deal with most of the cases, at least.
Okay. Maybe it's a silly question from me, because I know a little bit about convolutional neural networks, but I never heard about a YOLO type of algorithm. Could you maybe just quickly describe what is a YOLO type of algorithm?
Okay. YOLO is an acronym for You Only Look Once. It's actually a successful branch of object detection algorithms that work really fast and reliably. Like basic function of YOLO is to detect an object in terms of providing a bounding box in which the object is enclosed. With newer versions, you also have this option for segmentation of the object inside the bounding box. So it will not only tell you, hey, the object is within this rectangle, but it will also give you clear delineation of this object. It's actually quite famous. I think that we got version 8 now. So we had version 1, version 2, then was version 9000. Then was 3, 4, and there's a lot of varieties of YOLO, YOLO R, YOLO X, and because this algorithm is quite widely known and is being used as a base to developing some more application-specific things, like for example, small objects, remote sensing. It needs to be more sensitive towards small objects, and it needs to provide rotation invariance. So people modify it in order to provide those capabilities, right? I think if you look it up, you come up with lots of resources. I think it's quite popular.
Sounds very interesting. I'm sorry, I'm seeing another question. How possible it is, in your opinion, to adjust the robots to use in other plants?
I have thought about using a similar robot, because actually it was an idea from a company that built the robot for us, that they were contacted by someone who who grows blueberries, and they were thinking of building a robot to treat blueberry bushes. Obviously, that would be smaller, less tall, but it will also have this inverse U shape. And they were contacting us because they were saying that, okay, they can make this mobile robot base, but in terms of navigation and maybe those end effectors that will be used for picking the fruit, we'll have to, cooperate with them. So that's one idea. I know that similar robots are being used for a lot of things. Like I thought about pollinating. I'm not really, I can't remember what plant it was, but I have seen such robots used with UVC lamps, for example, to eliminate some fungal growth on grapes. I've seen such arrangement of robots used to spray different substances on plants that are in the form of bushes of singular plants. Obviously, this gives you a great potential for whole plant penetration. You're not only spraying from above, but basically from every angle. So I think that the potential is there. It's still a field that's being developed. It has a lot of promise, and actually quite excited to start working on that. We were basically, before we were working with drones in this project, although it's been really difficult, it's also quite satisfying. Like, I think we made the first step towards doing a lot of more complicated things with that.
Thank you very much. So I think we are ready for our coffee break, and we will reconvene at 11:20 for the next panel. Thank you very much, Jerome and Marek, for your interesting talks, and see you soon on our next session.
Thank you.
You're welcome. Thank you.
Everybody, good morning. So I am Lucia Riabov. I am a postdoctoral researcher at Vistamilk. So I work in data analysis from sensors to improve cattle welfare and health as well. So I will be the chairman for this session. So as in the previous one, we have 2 talks in this session, following by a time for questions